Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we'll continue with more hands-on sessions. Both thermocalc console mode and graphical mode we'll use and see how to plot property diagrams today. So these are the things we are going to plot today, G versus X diagram. There can be other properties that one can plot, like let's say viscosity, thermal conductivity, and many other properties that are possible. From thermodynamic properties they can be derived. But drawing thermodynamic properties is something straightforward. So for the education purpose, we will start that and do that. G versus X diagram we'll plot now. And you have done several exercises already. We have seen in the physical metallurgy and thermodynamics connection, applying thermodynamics to materials part, where we have seen how Gibbs energy composition diagrams underpin the phase diagram. So here we will calculate phase diagrams, we will calculate G versus X diagrams and see how they connect one to one, and we will see how to use certain features in the software to do this. Okay, so changing reference state is one by which we can get several things. One thing that we can get from that is mixing quantities. We will see how to get that. Right, so this is going to be our exercise now. CRFE G versus X diagram at two different temperatures, 1500 and 1000 Kelvin. Two different trees will form and do that. Then compare with the phase diagram. One more tree will make a phase diagram there and compare all the three one to one. Okay, these are the steps in the software. In thermocalc software, use graphical mode, open a new project, use one axis template, and three steps are there in that. You can define FEDemo database and FECR elements. You can select FEDemo database and FECR elements, and in equilibrium calculator, set condition temperature as 1500 first and set the axis definition mass percentage of chromium going from 0 to 100, and then perform calculation, which is a step calculation. And this step should be a specific type of stepping. It's going to be separate stepping. Okay, because we are going to get the Gibbs energy composition plots, it's good to choose separate stepping option, so that for individual phases we can get the Gibbs energy versus composition diagrams. So that we need to do here, and then in plot renderer we can visualize the reports. We are going to do one more thing: clone this tree and set temperature as 1000 Kelvin and repeat. Okay, and make CRFE phase diagram and compare all. Let's do that. Okay, so now I'm going to click on one axis template. Database FEDemo is fine. Select elements FECR, FE first, CR second, and then go to equilibrium calculator. Here set the temperature 1500 in the top, 1500 Kelvin, and here in the axis definition select mass percent of chromium from 0 to 100. And the important thing is the step method, change it from normal to separate phases. We have done it previously for G versus T diagrams. Here we are going to do it for G versus X. Okay, then go to plot renderer. Here volume fraction of phase is there in the y-axis by default. We would like to change it to Gibbs energy, and no normalization should be changed to per mole. The reference state can be left in SCR. This SCR checked here, this is basically the reference state. By default, standard element reference is chosen. In the upcoming exercises in this class, we will try to change it and play around. And then the energy, Gibbs energy, is for all phases in the system in joules. That's all. Then we can click perform either here, or we can go to equilibrium calculator and click on perform tree. Both are fine. So I'm clicking perform tree here. Okay, the diagram has come. can see gas phase Gibbs energy is there in the top. All other condensed phases are here, liquid and other solids. I can just put a small box here, drag and put a small box and leave it. I can see the Gibbs energy of all the phases. The green one here in the bottom is dominant almost throughout, that is BCC. The left extreme, this orange curve becomes lower, which is FCC Gibbs energy curve, that is appearing here. We will compare these two phase diagram and understand. Okay, so we will make two trees now. One tree, right click, clone tree. Okay, clone tree. Now the tree is cloned. One change we will make here, that is in equilibrium calculator, we'll keep the temperature Kelvin 1500 to 1000. No other changes. Okay, we'll simply click perform, so that we'll have G versus X at 1000 Kelvin in this tree. Let's have that also. Right, we have it here. I'll just zoom into this zone just to show you that this green curve is there in the bottom but not throughout. There is this dark purple line coming, plunging below that, which belongs to sigma phase, and in left extreme also green curve is the only stable phase, meaning the orange curve, the FCC curve, doesn't cross and becomes lower. So therefore BCC is stable here, but in the middle sigma becomes stable. Okay, you can see that. Now let us make the phase diagram and check that. I'm going to click on my project, left click, and I see the configuration window now is giving me all these options. I'm going to choose phase diagram. Okay, so in phase diagram I'm going to click FE first, CR second, then equilibrium calculator. My temperature range should be between 1000 to 1500. Okay, so if 500 to 2000 if I make, it is good enough for me to compare. Okay, 500 to 2000, mass percent of chromium in x-axis, click perform. Right, the familiar FECR diagram is here, and what we want to check is whether at 1000 the BCC is stable from very left extreme. Here you can see BCC is stable for a big range, and then BCC and sigma both become equilibrium phases for a range. Then it is only sigma for a small range. Then it is only sigma for a small range, and then again it is BCC here. Okay, this entire region is BCC if you remember. Okay, so this side is again BCC. So are we seeing this? Are we seeing single BCC, then sigma plus BCC? This should come from a common tangent in the Gibbs energy versus composition diagram, and this sigma phase should be stable for a small range, and then again two phase region and again single BCC region on the left side. Are we seeing this at 1000 degrees result? Let's go to plot renderer 2 and see the results. So this is where we are. The green one here is the Gibbs energy composition plot for the BCC phase. It's labeled here. Green one is BCC-A2. Okay, and then the purple one is sigma. You can see that the sigma is plunging down. I will just zoom into this zone alone. You can see here. Okay, so you can put a common tangent between this sigma and green curve BCC like this, and read couple of compositions here, and that corresponds to the two phase region. And then in the right side of this purple curve also, this green curve and purple curve can meet in a common tangent, at two different points, and they correspond to another two-phase region of sigma plus BCC, and in the middle there will be a small composition range where only sigma phase will be stable. Okay, you see that, and the other, let me zoom into that again, and anywhere far beyond this common tangent you will see that the BCC phase is coming. So of course I am not plotting the common tangent here, because that is the procedure done by the software when we calculate this phase equilibria, phase diagram. Okay, at multiple temperatures or for all this composition range it is done. So you could sense what is happening in the software behind. And if we go to plot renderer 1, 1500, you see BCC is completely dominating. In the left extreme, you see the FCC becoming stable. I'll zoom into this area and show you. You can see that there is a crossover between orange curve and green curve, and orange becomes the lowest at these compositions. Okay, so that's why you see in the plot renderer 3 the phase diagram at 1500 somewhere here. You can see from left to right it is FCC in the left. You can see FCC, this is FCC region. So 1500 from here to here, for some range it is single phase FCC, and then a common tangent from in the G versus X diagram between FCC and BCC, then complete BCC. Okay, so that common tangent you can draw here in plot renderer 1. Okay, if I zoom into this zone, you can sense that there can be a common tangent coming between this orange curve and this blue green curve for a small composition range. Okay, that is going to be the small two phase FCC plus BCC region. Okay, so that is somewhere between 6 to 12. So in that range you can see a common tangent, and that 6 to 12 here you can see somewhere here 1500. Okay, within that 6 to 12, strictly speaking it is 7 to somewhere around 9. That's the range over which you have two phase region. Okay, common tangent comes there. Right, so now you can see how one-to-one phase diagram and G versus X compare in Thermocomp software. You could see that, right? So now what we will do is, you can see these curves are starting from somewhere and going somewhere here. It's not looking like a nice curve starting from two equal points. Okay, if they are starting from two equal points, we can say this is entirely Gibbs energy of mixing, because we can put a horizontal line between 2 points and call it the reference energy level. From there, how much we get down, that is the mixing Gibbs energy, right? So we can see that in the diagram, provided both the points are starting from 0, 0. Okay, so how do we make that? We can make that change by changing the reference state. Let's see how to do that. How to change the reference state of Gibbs energy, that's what we are going to see now. Okay, change the reference state of Gibbs energy to visualize the Gibbs energy of mixing. This is one purpose of changing the reference state. There can be many other purposes depending on your usage. So right now we are going to visualize Gibbs energy of mixing. To visualize Gibbs energy of mixing, make whatever is the Gibbs energy now for these two elements, chromium and iron, whatever is the Gibbs energy, make it 0. Okay, therefore whatever is the current state is going to become the reference state. Therefore it will become 0. So to do that, the procedure almost remains the same. Only thing is in the system definer stage, we have to select reference state for both the elements Cr and Fe to be BCC at current temperature. Pressure is fixed here, so we are not in graphical mode trying to change that. Cr Fe, the state reference state should be BCC at current temperature. Then in plot renderer, uncheck reference state SCR, so that the state that we have set will be taken up. Then click perform. Let's do that. So we are going to clone tree from previous exercise and do this. Okay, so only for one temperature I will show that. So let's take system definer 2 and clone tree. Okay, we are going to get one more tree. Okay, the one more tree has come here. This is the fourth tree. System definer 4 equilibrium calculator. So we are going to go to system definer 4 and do this change of changing the reference state, setting the reference state. How do we set that? In the top there is this fourth tab called components. Okay, click on that and you can see Fe, Cr, two components are given and SCR is checked now, uncheck SCR. We are going to remove the standard element reference. Okay, and then once we uncheck it, we get this phases appearing here, reference phase. So reference phase is going to be BCCA2 for both the phases, both the elements. And then reference temperature, current temperature is checked, we can keep it. Okay, then Pascal's pressure, we will not change it now. Okay, that's all. Then plot renderer 4. So go to plot renderer 4, then change this SCR. This SCR is checked, uncheck it. That's all. That's the only change. Then you can click perform tree or perform. Yeah, now you got this diagram. Okay. If I zoom into this, you can see I'm going to go to the bottom. Other phases are not that important to us. Okay, so you can see now from 0 it starts and it goes to 0. Okay, this is both chromium and iron are going to have this 0 value for Gibbs energy now, pure elements. So that's the reference state now. At current temperature, whatever is the Gibbs energy is now made to 0. Therefore, whatever we are seeing in this curve is only due to mixing. So what we are plotting is only Gibbs energy with a different reference state, and now this Gibbs energy has become Gibbs energy of mixing. Okay, so that's what you see. And sigma phase, you can see here nicely it is plunging down. This kind of diagrams is what we have seen when we applied thermodynamics to materials and understood how Gibbs energy underpins the phase diagrams. Okay, so you can see that, right? So this is how you change the reference state in graphical mode, right? Okay, so now we are going to use console mode and do that. Quickly I will show how to do that. So the important change is here. We have seen that in previous class when we made the COCR FENAV phase fraction plot, that we used stepping instead of mapping and set only one axis variable instead of two axis variables compared to a phase diagram. That's the important change. So we'll do this diagram first, and then we will do another exercise where we will use the macro and change the reference state. So to change the reference state, we will use the same file so that you know how to use the macro file. You have been setting log files for such a long time. We haven't used them and use as a macro file, and see how small modifications in that can lead to new exercise altogether. Okay. Let's see that. So I'm opening thermocalc. Okay, I'm clicking on this switch to console mode. Okay, set log file gx. Okay, enter, heading also gx, then go data, we are in FE demo, define system CRFE, enter, then type get, enter. Now go poly, enter, set diagram axis, set condition, pressure equals 1E5, number of moles equals 1, temperature equals 1000, and x of CR is some value, let's say 0.1. That's all. Then list condition and see whether degrees of freedom are 0. Yes. Then set axis variable 1 is going to be x of chromium changing from 0 to 1. That's all. Okay. Enter. No second axis variable. So just go step. Step is like mapping but only in one axis variable. Step. Option normal stepping. No, we need separate stepping. You can put a question mark to check that. You can see normal stepping, separate phases stepping, There are other options, T0, mixed shale and all. We will see them as we go along. This is what we need now, separate phases. Type SEP, that's fine. So now the stepping is done. We can go to post module, post, set diagram axis X, weight percent of chromium, okay. Then set diagram axis Y is going to be GM, Gibbs energy of phases. There is something called as column number, but do not bother. Gibbs energy of all the phases is what we are plotting now. Okay. That's all. Then plot PL, enter. Okay, you got the Gibbs energy of all the phases now. Okay, they are not labeled. We can use set label curve option space F, then plot. Okay, now it has given a number to each of these lines and explaining here what are each of the lines correspond to what type of phases. Okay, so the numbers are given here. You can see the exact you can see the curves and understand what is what. Okay, the number 10 is the sigma phase. You can see this one, and this long line is the green line that we saw in the graphical user mode, which belongs to BCC number 3. Okay, so you can explore in the post module. There are, if I put a question mark, there are multiple options coming. Okay, there's so many things you can do in this diagram. You can select if you want colored lines, or let's say you want dotted lines for something, dashed lines for something, and still keep everything in grayscale, let's say black and white without any colors. You can do that. All options are there. And there is something called data plot user guide. If you go to the help manuals folder in thermocalc here, help manuals folder, you can see that these manual folders are there in your local computer. You can open it and see data plot user guide, and that will have guidance for all these different changes that you can do in the control mode post module. Okay, right. So now we have plotted this diagram, and what we will do now is we will try to change the reference state alone and plot the diagram again. Let's see how to do that in console mode. Exit this console, documents folder where the log file is saved. I'm going to open this GX. Here whatever we have typed are here. In fact, after after list condition, we should have done compute equilibrium. We have not done that, and still it works. So you can type compute equilibrium for the sake of completion. So then this is what are all the syntaxes we typed. These question marks I typed just to show you what syntaxes are possible. So I'm removing them. This exit we don't need now. And then this is what the syntaxes we have used. Now after list condition, we can set reference state S-R-S, set reference state for element CR. So space CR, then space what phase, BCC A2 is the phase, then what temperature and composition, current temperature, current composition. So 4 commas, that's all. Then set reference state for iron, space BCC A2, current temperature, current pressure. Okay, after all this, type set interactive. It will keep the window alive after executing the task, otherwise the window will exit on its own. Okay. Then one more change we need to do, that is the set diagram axis Y is now GM. GM is Gibbs energy per mole. Okay, we are going to change Gibbs energy per mole with respect to the reference state that we have set. So we have to type GMR. Okay, now Control S, save it, then open thermocalc. Here you can type simply macro, or just M is fine, then enter. Then open the documents folder where this particular file gx.tcm is saved. So click that gx.tcm and open. That's all. So we required few changes to do in this calculation compared to the previous calculation. So take the macro file from the previous calculation, add things that you want, edit things that you want, then plot the diagram. Now you got the diagram. If I zoom into this zone, I will see that the BCC curve starts from 0, ends at 0. You can see curve 10 is for sigma, curve 3 is for BCC A2. Okay, curve 3 starts here at 0 and goes up to 0. You see, so this effect that we have made has taken place. You can see set diagram axis Y is GMR, not GM. And if I see in the top, reference state, set reference state chromium BCCA2, set reference state iron BCCA2. See, so these are the things we have made, the changes that you have made in the TCM, and they are reflecting here. So this is the biggest advantage of console mode, where you can do small changes to one of the previous files that you have that you have used for different calculation, perhaps for a different element, perhaps for different conditions. Okay, so you can change them here and execute them like this. Okay, this is one of the biggest advantages. Yes, thank you. I hope the lecture is useful. See you in the next class.